So now let's look at some of what we have already talked about. We're going to be talking about first of all, we're going to be talking about the binomial distribution. So here's an example now. A doctor is testing a new drug that has a 90% success rate. So this is our P. He now treats 20 patients and wants to know the probability that exactly 18 patients are going to be cured. So 20 patients is going to be our N, which is the number of trials, and he wants to know the probability that the example exactly 18 patients will be cured, which is going to be our random variable X. So now what we do, we know that our N is 20 and our P is 0.9, which is probability of success. So run this. We're now going to use the calculate the probability by using the d binom function. So that particular binom function we used earlier on is just to create a vector of values that are following a particular distribution. We have binom, which is for creating a vector of values that follow the binomial distribution. But this d binom is more or less like the formula. So a formula to calculate the probability itself. So now this d binom that you are seeing now, first of all, we are going to be giving our random variable, which is x. Then our size argument is going to be the n, and the probability is going to be p, which is 0.9. So when you run this now, you get 0.285. So this 0.285 is now the probability that exactly 18 patients will be cured out of 20 when the success rate of the drug is 90%. Now, suppose the probability of a positive result for a genetic order is 0.1 now. This is the next example, which is going to be our P, and 15 individuals are tested, which is going to be our N. What is the probability that exactly 3 individuals is tested positive? So 3 is going to be our X, random variable X. So just like before, N is going to be 15, P is going to be 0.1, and we use our d binom function and provide the relevant arguments where 3 is going to be our random variable X, and we run it, we have 0.129, approximately 0.129. So our probability that 3 individuals test positive to the genetic disorder is 0.129. Now for the Poisson distribution, and I'm told that the Poisson distribution uses a parameter lambda, which is the average of an event occurring within a particular interval. And so on average, the hospital experiences 4 attacks per day, and probability of having exactly 6 attacks in a given day. So lambda is 4, which is what we have, and the next variable, we just need only 2 variables for the Poisson formula, which is d pois, and we have to give our random variable x, which is 6, and we give the value of lambda, which is the lambda argument. So when you run this, you can see that probability of having exactly 6 attacks in a given day is 0.104. So now the next we have is on average 2 cases of hospital acquired infections are recorded per week. What's the probability of observing 5 such cases in a particular week? So let me give some moments. Pause this particular video. What is your lambda? Lambda is 2, as you can see, and our random variable is x is 5. So we're going to be giving these two variable values. We'll put it our d pois function. You can see that we have the probability of observing 5 such cases in a particular week is 0.04. Now for the normal distribution. So suppose systolic blood pressure in the population is normally distributed with a mean of 120 and a standard deviation of 15. So what's the probability that a randomly selected individual will have a blood pressure between 110 and 130? In this particular case itself, let me also explain something now. You can see that we are saying probability of exactly 18 patients will be cured. What if they now say what probability that less than 18 patients will be cured? How do you do that? Now, you have 2 ways of doing that now. Probability that less than 18 patients will be cured means that what's the probability that 17 patients will be cured? Probability that, because less than 18 patients means that 18 is not included. What's the probability that 17 patients will be cured? 16 patients will be cured. 15 patients are going to be cured. Up to 1 patient is going to be cured. What is the probability? You're now going to add all these probabilities together. That is the first approach, which is really tedious. The second approach is that why don't I find the probability that at least 18 patients will be cured, which is probability of 18 patients will be cured plus probability of 19 patients will be cured plus probability that 20 patients will be cured. Once I find that probability, I subtract it from 1 to get the complement of probability of less than 18 patients will be cured. So what I'm going to now do now, I'm just going to say d binom, or let me just copy this and I'll bring it here, which is going to be 18, and I'll say plus here, going to be 19, plus going to be 20. So this is the probability at least 18 patients will be cured. So when we run this now, when I run it now, I called probability of at least 18. You can see I have 0.68. So this is the probability that at least 18 patients is going to be cured. Now, I now find my question is asking that probability that less than 18 patients are going to be cured from that particular vaccine or from that particular drug. Now, I'm now going to subtract this from 1. So probability less than 18 is going to be 1 minus probability of at least 18. So when I run this, I have 0.323. As you can see, so this is the probability of less than 18 patients are going to be cured. This approach I explained to you is what I'm going to use even if you face that same issue in the Poisson. You are asked what is the probability that at least less than 6 attacks are given in a day. Use this particular approach, and I would like you to also try that as a practice exercise. So this is what you do when you face this kind of dilemmas. So now back to our normal distribution. You have to calculate probability that a random selected blood pressure individual will fall between this particular range. So what do? First of all, now we are told that the mean is 120 mmHg and millimeter mercury, and we have the standard deviation of the blood pressure is 15. Now for us to find the blood pressure that probability of this particular interval, what I'm going to do, we need to find the probability of 110 first, and we'll find the probability of 130. So now in the Binomial function, we'll first of all find the probability of 110, 130, which is this. So first of all, we have to run this. And let's find the probability of having a blood pressure of 130, which is 0.75, and the probability of having a blood pressure of 110, which is 0.2. So to find the probability that falls between this interval, you subtract it. You can also apply the same approach to the binomial if you are asked probability between a particular interval. So let's load the NHNES data now, and I'm just going to be taking the ID, the total cholesterol, and the age columns, and I'm going to be removing any missing values there, and I'll calculate the mean of the cholesterol. I'm showing you how to standardize a variable now. I explained the standard normal distribution earlier on that has a mean of 0 and the standard deviation of 1. So I'm going to take the mean of the cholesterol and take the standard deviation of the cholesterol, and now I'm going to be standardizing the cholesterol level. So I'm going to be using a z-score this time around now. So if I take that now, so if I check the head of the cholesterol level data now, let's look at it. So this is our total cholesterol, which is the normal value, and this is the z-score, the standardized z-score, where we subtract the mean from each observation and divide it by the standard deviation. You can see what we have. So now we also have another function now. Instead of writing this particular formula, you can just use the scale function. The scale function also standardized. You can see you have something similar, minus 1.2. Now you can see we have something similar to what we have. So you can use the scale function to also to create a variable. So now if you check the mean of that particular column now, the mean of the z-score column, so the mean of the let me see, cholesterol data, the z-score column. So you can see this is approximately 0. As you can see it here, this is approximately 0. And if I check the standard deviation, SD is 1. So you can see that we already standardized that particular variable. So it's now a standard normal distribution. I also give you a practice exercise. Try and plot the histogram and see how it looks like. You're going to see that it gives you a bell-shaped curve. So we have another example here. Birth weights of baby in a certain population are generally distributed with a mean of 3.2, which is our mu, and standard deviation of 0.6, which is kg, which is our sigma. So what is the probability that a randomly selected baby weighs between 2.5 and 4.0 kg? So now our mean weight is 3.2, standard weight is 0.6, cumulative probabilities, which is p norm, is going to be 4.0, and that of 2.5, which is going to be this. Then we subtract that of 2.5 from 4, and we get the probability, which is 0.79. So this is probability that a selected baby weighs between 2.5 and 4.0 kg.